Good morning, folks. This is lecture 2 of week 5. And on the agenda today, we have the brand new topic of hybrid mesh analysis or hybrid analysis. And as an example, I will do chapter 19 in the book. However, I caution you that if you're looking at the book, the way I create my surfaces and beam elements is completely different from what I'm doing here. Okay, I stopped doing it like it's in the book, so you will see that difference. Now, let me tell you what the problem is. What does this hybrid mesh analysis mean? First of all, chapter 19, what are we dealing with? We have a structure like that. The minute you see the structure, you should see that this needs to be done with solid element, this has to be done with shell element, and these with beam elements. Okay? Now, there is a question here. What if actually, and these connections are all welded, perfectly bonded, okay? For example, the edge of this, plate is completely welded to the surface of this cylinder, and the corners of these, this support and that plate are all perfectly welded. Now, the question is, what if these are actually cables? In other words, actually they're not welded together. Maybe there's a hook there, it holds it, etc. We'll do that later on. Now, the dimensions are given there. On purpose, I made this beam element. In other words, all three have to be used: beam element, shell element, solid element. And on purpose, I made the cross section of this beam element to be square, not a circular cross section. Therefore, there is an orientation point that you have to discuss. Now, the question becomes: oh, by the way, the bottom of this cylinder is clamped. The top of these two supports are clamped, and this surface is subjected to a pressure of 100 psi. Now, we'll come to this in a minute. I want to show you why is it important actually to do hybrid analysis. Why do we have to use mixed elements? For example, do you remember this problem is a thin wall pressure vessel or a pressure vessel in general? Now, at the seam, there's a lot of crazy things that can go on because these are where the bulk of the stress is. And if we do it with shell element, unless we take a very, very, very fine mesh around these circles, the results are not very reliable. Not only then, even then, the assumption for shell is that the stress through the thickness is zero. Well, if these are, that in that vicinity, that may not be the case. So what people do is actually they have a geometry like that. I mean, obviously you can make this thing entirely as solid, but it's not going to be effective because there's going to be so many elements through the thickness that it becomes impossible. Now, the alternative is to use in the vicinity of those edges solid elements, and everywhere else shell elements, which are reasonable. And this is what it means. This is what it means when we say that we're using mixed type of elements or hybrid mesh in general. It could be also that, for example, we have beams in this case. So I'm going to go to this problem. This problem can be done either entirely as a single part. Single part consists of all these pieces, of all these things, or I can do it as an assembly of several parts. For example, one part can be the cylinder, one part can be that plate, one part can be these two lines, etc. Today, I will not do it like that, but in tomorrow's lecture, 50-minute presentation in the lab, that is how I'm going to be doing it as an assembly. It's entirely up to you how you want to approach the problem. Either way, acceptable. If you're asked to use as many planes of symmetry, you should realize that for this case, I need to make a cut along that line. So half on this side, half on that side. So today I will actually do both of them. I will do this problem as a single part. However, I will do both as having used planes of symmetry and one That is not, because I'll do both. But however, tomorrow I'll do the same problem as an assembly. Okay, so the dimensions are given. Let's go ahead. Since it's a single part, I'm going to start making it. First, without any planes of symmetry, so I'm going to make the whole model. So I'm going to make a part. Okay, on a convenient plane, on that plane, I'm going to sketch something that looks like that. Okay, let me try to make it a rough sketch, and then we clean it up in a minute. Okay, so this left line, control right line, control middle axis. I'm going to make it symmetric. Let's dimension these things. This is 2 inches. This is 2 inches. And there's a circle here, a hole of, I believe, radius 0.5. Radius 0.5. Okay. Exit. Now, I want to put a surface through this. Remember, in the past, we have drawn a sketch and put a surface on it. The problem is that with the current version of CATIA that I have installed on my computer, this surface cannot be like that. It cannot have this hole. On the university installation, you can do that. So what I'm going to do, because I have to show you here, what I'm going to do, I'm going to pretend that actually you don't have it at university either. So I'm going to go back to that sketch and delete this. There are many ways of doing this. I just don't want you to be stuck with the way I'm doing it. So we want to put a surface through this. So what we do, we go to, as soon as you say surface, you have to go to shape, generative structure, generative shape design, and fill. Please note that there are other ways of doing this thing also. Now, on that face, I will sketch that circle of radius 0.5 that I wanted. Radius 0.5. We say OK. Exit. And there is this split here. There is the saw here that you can cut that surface with the circle. With the newer version of CATIA, see, element to cut is sketch. Actually, element to cut, let me cancel that. Make sure that nothing is selected. Element to cut is that surface. Cutting element is this. With the newer versions of CATIA, you can have actually the original sketch with a hole in it and fill between the two, but I can't do it on mine. Okay, good. Now, the next thing I want to do is, we basically created this. The next thing I want to do is to create these lines, because these are going to be meshed with beam elements. So here's the way I'm going to do it. You do it any way you want. So I'm going to make a line, and the way I'm going to do that with a point and direction. So the point is that point. The direction is along the Z, and the height is I believe 3, right? Was it 3? Yeah, 3 inches. Okay, is that good? Yeah, okay, fine. Now I do the same thing on this side. So another line, point and direction. This is the point. Direction is Z. Same thing, 3 inches. So that takes care of this, basically, these two. Now the solid cylinder. Now the solid cylinder actually, it's entirely up to you how you want to do that. But here, first of all, I'm going to go to part design, because it has to be solid object. So on that face, I will sketch. I want to sketch a circle that size. So why don't I just actually project that on it? there. It's projected, exit, projected, you can see that. And then I pad it in each direction by 1 inch. There we are. So we have generated this geometry. Everything is made out of steel, so we go to apply material. This is a single part, so to say that everything is made out of steel doesn't make sense. This part is made out of steel. That's really what I should be doing. Okay, now we're going to go to generative structure analysis. Immediately that the cylinder is going to get meshed. So you can see that. Right click, mesh visualization. There we are. Change the rendering. There. Now the other guy, let me hide this, deactivate that to see the other pieces. Okay. Notice that here, if you look at this this thing, it looks like I've gone to the advanced meshing tool and got a four-sided. Unless you're asked to do that, it's okay. You don't have to. You can just go ahead and measure it with standard octave triangle measure, okay, which is this. I'm not suggesting you go there, advanced meshing tool. There's some basic stuff you should be able to do that, but on the absence of any instructions, you can do it here. So I just noticed something. Yeah. Okay, so let's check that. Right click mesh visualization. Wait a minute, what happened here to my let me undo this thing because it looks like something went nuts. Let me delete this, try it again. Okay. Select this. Select that surface right there. Now it's better. How about 0.2? Say okay. Activate. Now you're going to see both of them, the shell and the solids. Good. So let's deactivate this. Can do it from here. Why don't I give a thickness here? The thickness of that plate we're told is 0.1 made out of steel. Now we're going to have to mesh these with beam elements. So you go to beam elements. There. Why don't I, this was 3 inches, and why don't we take 1 inch, well actually let me make 0.1 for a reason that I want to show you later on. 0.2, so that's going to be about 15 elements through that through that length. Let me make it 0.2. Okay, good. You say okay, and if you look at it, you see that you see that that's also there. These beam elements are also here. Deactivate once again. Do the other side. So mesh this side. I didn't have to join because this was a wireframe. It was done as a line in space. Don't forget that if you're using beam and you're doing it in sketch, you have to join first. Now, the cross section. The cross section, we are told that it is, first of all, rectangular. The size of it is 0.05 by 0.05. 0.05. And then it says, what is the support? Let's start with this one. Notice that I can't close it because it's expecting to me select the orientation point. The orientation point, I'm going to select this point on this side. Zoom in. If you're having a problem picking it, hide the sketch. Hide the sketch. Yeah, now I can do that. And notice that when you do this, it rotates this so that it lines up the way it's supposed to be. Okay? You can pick other points too, but I mean, I'll leave it to you. Another one on this side. Again, the rectangular, the size is the same, and orientation point is this guy, this corner point. If you're having a hard time, hide this, select that corner point. Wait a minute. Let me see for a second. Okay, so actually let's go select the bottom of this fellow. Let me bring this thing in the front. Hide that surface. I'm pretty sure I can select this. Wait a minute. Let's see if it did it. Oh, you know what? Actually, the problem is this. Cancel that. Cancel that. Let's try it again. Cancel. 1D property. Select that support because I had picked accidentally the other one. And then rectangular 0.01 orientation point. Now I can select this point. Oh, it's the other one. Yeah, it's the other one. The reason it didn't work the first time is that I accidentally selected this line, which I already defined as properties, and then I tried to select that point. Remember, the orientation point cannot be on the line or on the continuation of the line. I mean, if you look at it closely, you see that this is exactly the way it's supposed to be. Good. All right, everything is made out of steel. We already did that, no problem. Okay, so now we're going to go and if you look at the mesh, you're going to see these meshed. Everything is meshed. So clamp that top point and this point and the bottom of that. Okay, very good. The top of this is pressurized, 100 psi. Make sure it points in the way you want it. Let's see now, did I pick it? I haven't picked it yet. What's this pressure? Yeah, right there. Yeah, right there. Now this should be negative now because pressurized down. Good. Now, if we run this thing, it's going to fall apart because these guys do have no idea the other fellow exists. Okay, so let's try it, run it, and you see that actually it goes nuts, moves as a rigid body. If you look at the deformation, for example, you can see that nothing is connected to nothing else, to anything else. All right, good. So deactivate this. Let's start that connection. So between the end of this, the point at the bottom of this line and that corner, one connection, same thing on this side, and those should be rigid. Point to point connections must be rigid. Okay, so first create a connection. Let's not worry about what it should be. Let me hide this point, and for the second component, the corner of that, the only thing is that notice that this sketch is blocking it, okay? So let me bring this in the front. If there's any possibility of making a mistake, hide the stuff that you don't want, hide it. Still won't let me pick it because this connection, you see that, is still blocking it. So that connection that we are trying to find, to make, let's hide it. And now I can select that corner, okay? Do another one. Do another one. Let me hide this. You have to do this thing patiently. I mean, you just cannot rush. Bring this in the front. I'm trying to pick this point. Now I don't know when I do it like that. I don't know whether I'm picking it from the line or from this. So I can't even remember which one I picked. I can't remember. Let me remove this. Let's try it again because I forgot. So this one, I'm going to hide the surface. First component. So this is the line. Now I go and bring this guy into the show mode, or you can hide the sketch and select that corner. That's entirely up to you. It's just that the sketch will be here, which doesn't bother me, but let me bring this in the front. Okay, sketch ended up here. I don't want it. I have to hide it. Anyway, these are the rigid ones. So rigid is part of distance connection property. Point to point is rigid. Okay, so rigid is right here. This is rigid. This box is very important. I'm going to come back to it later on. and another rigid. This guy is rigid. Okay. Now the edge of this circle here from the plate and the surface of the cylinder are perfectly bonded, welded, perfectly welded. So first of all, let me hide that sketch. Good. Another connection between the surface of that cylinder and that edge. If you think you picked it, and I think I have, you selected it, and this is going to be fastened. Fasten is face-face connection, right there. Face-face connection. Contact is here, fasten is here. And you select that. Notice that it does put a fastener sign there. And we're going to run it. This time it's going to work, and we're going to see how things went. Good. Look at the deformation. There we are. Animated. Now, if it's bothering, if it's not showing anything, that's because, remember, we already asked it to show us something that went to infinity. So make sure you go to the scale and default. Use default right there. Okay. So there it is. Okay. That's the way it should be, right? That's the way it should be. Now let's look at the displacements. Average ISO, material shading. There we are. Okay. Yeah. There is a displacement in this cylinder though also, and if you want to see it, you just select it. For example, look, on the selection, just showed me the cylinder, oct3 tetrahedral. There we are. You can see that there is a displacement. Okay. Now, one thing you might say, well, first of all, if you plotted the von Mises stress, we're not going to see anything in the beam. That much you know. That much you know. But the thing is this. Let's go back here. Cancel that. Let me go back to a displacement instead of von Mises. So deactivate this, activate that. Because I want to ask you something. Oh, cancel, activate. Okay, you might say, okay, if you look at the front view, first of all, you see there's a symmetry here, right there. You can see that. But then you might say, well, wait a minute, this can't be a cable. And you're absolutely right. Because they are welded at this location, they don't act as a cable. If you want it to behave as a cable, what you do is you go to properties. Remember, I said I'm going to go back somewhere. Go to properties, double click on rigid, transmitted degrees of freedom. So you check it and you say, hey, wait a minute, rotations cannot be transmitted. This is a cable. So uncheck all of those. Do the same thing with the other fellow. Uncheck all of those rotations. Okay. Where is that beam? Let's bring it in the front so you can see it. They just let people get confused. What happened to it? It's right there. Now, there's only one more step that you have to do, because if you run this thing, this rotation cannot be transmitted at this support too, because let me run it to you. You see that up there it still bends. So let's run it. Okay. Look at the translation. You might say, wait a minute. See, at this point, all 3 degrees of freedom were fixed. Okay. Yeah. So in reality, what you should do there is you should go there, and instead of clamp, let me take this thing away. And put the user-defined restraint with 3 translations and spinning about Z fixed. This is really a cable up there, because the way we did it, that point on the top was also clamped in terms of rotation, but now we remove that. So if you run it, well, let's see, something did not go through. Let's check it out. Let's see what happens here. Look at the displacement. Okay, so we can see, let's animate this. Oh, remember I deleted the clamp? The clamp at the bottom was also part of it. So, okay, that's what happened. Remember I deleted these clamps? That took away that bottom clamp also. That bottom clamp is fine. Now it's going to run. Yep. So activate. There we are. Average ISO. There we are. And let me actually say default right there and animate. You might say, wait a minute, this didn't change that much. It looks like that's what we had, but not really. The, there will have been differences on the top here, but I basically turned that thing into, by saying the three translations are fixed, made it into a hook. The thing is that with a hook, it also allowed to, or a pin, it's allowed to spin about the Z axis. I took away that. If I don't, then that may not run. You can see, let me go here. Let me go back there under this restraint, double click and take away that spinning motion. Let's run it now. I'm pretty sure it's going to bomb out. Yeah, we can see that because it has the ability to spin about this line. Okay, so I did this problem. Now I'm going to repeat it, this time as an assembly. And we have time to... Oh, sorry, I didn't mean as an assembly. I meant to use planes of symmetry. That's what I meant. Assembly, we're going to do that tomorrow. I'm going to do it in the lab tomorrow. Okay, so let me get rid of these. Okay. And I have two choices. I can go to the assembly. Well, I really... I want to use planes of symmetry, and I can use it here. I have two choices. I can either I can repeat the whole thing, or just cut it with the appropriate planes. For example, let's see. Uh, let's say we want to split this cylinder. Well, we're in part design, so we use the split here. It says, what do you want to split it with? I want to split it with that plane. Is it the left side or right side you want to keep? It doesn't matter. I'll keep the other side. There we are. Now I want to split this uh, surface. Now I can't do it with this guy because this only does solid objects. So what I'm going to do is I'm going to go to generative shape, generative shape design, get the split there, find a saw there, and please make a note of these things if you need it on the test. You don't have to start looking if you feel like it. Put it under operations toolbar or something like that. Here's the split. It says, what is the element to cut? The element cut is that entire face. Cutting element is that thing, is that plane, right? But it's not this side that I want to keep. I want the other side there. And you say, okay, good. Now, as far as meshing this line is concerned, I can leave it the way it is. Just now, I don't have to use it. I'm not going to mesh this. It's just like you might say, well, should I delete this? You don't have to. Just don't mesh it. That's as simple as that. So we're going to go to analysis and simulation, generative structure analysis. CATIA sees a solid object. Immediately, it meshes it right there. You can see that. This is the cylinder. Right-click mesh visualization. Half the cylinder. You can see that. Okay, deactivate it. Good. Now, we have to mesh the shell. So using the, octave triangle mesher, nothing fancy. Select that. I think I made this thing a little smaller, maybe 0.2. Still linear. Now, if you measure it, right click, if you activate the mesh, you see that the shell is going to pop up too. Both of them are going to be there. So once again, deactivate. Don't forget to give it a thickness. Thickness was 0.1. Okay. Now we're going to mesh this beam. Don't worry about that. Don't mesh this because it's not going to participate. Should not participate. Not this. Cancel that out. Let's try it again. Beam. Right there. And I'll use still 0.2. No problem. You know what? I'm going to make this thing, make it even smaller, 0.1. I don't have to, but I want to look at a, different size mesh. That's fine. Now, cross section. Select the support. There we are. It's rectangular. The size is the same, correct as before. For orientation point, I use the point on this side. If you can't pick it, remember that sketch that's causing a problem. There are other ways of fixing it. Let me hide that, and then you can take the bottom. And that is actually the way it's supposed to be. Say okay. Good. Now we come to the restraints. So first of all, we're going to use first beam and then we're going to turn it into cable. So this top is clamped. This bottom is clamped. And I'm going to do it separately so I don't run into the same mistake that I had before. Okay. This is a surface slider. And I cannot leave these restraints alone. These are symmetry for the shell. So user define these edges, this edge and that edge. I'll put down here symmetry so that I know what is what. Symmetry of shell. These two edges lie in the YZ plane, do not move in X, and rotations are exactly the opposite. So it's these two. You say okay. Then we have to create connection. Remember, if let's put the pressure there. Same pressure. Pressure does not, you don't divide it by 2 because you took half of it. Now, remember, if I run this thing, it's going to bomb out. I'm not going to do that, so I create my connections between these things. I'm going to hide that, between this point, and for the second component, I want that point. If I cannot select it, you can hide the sketch to get access to that point. Oh, not edge. Oh yeah, vertex. I did take the vertex. You can see it's orange there. You say okay. I can bring this thing in the front if it makes you happy. Okay, so this is rigid. So distance connection property, point to point is always rigid. If you try fasten, it will not work. It will bomb out. And there we are. And then the edge of this semicircle with that sheet and that surface of that cylinder. So another connection between the surface of the cylinder, and I'm going to try to pick for the second component. I zoom in. I try to pick that half a circle right there. Okay, and this is going to be fastened. You're told that the components are fully bonded, fully welded, perfectly welded, fastened. So fasten is right here. It's that last connection. We say okay. See the fastener sign here? Good. Now we're going to run it. Done. Look at the deformation. This is what we expect, right? And you can see the bending. You can see the bending. Yeah. And also, because I use a finer mesh, you can see that this actually comes out to be at 90 degrees. Whereas if it's a pin, it's not supposed to be 90 degrees. Okay, so we're going to fix that. Let's deactivate this block. Where's deactivate? Okay, let me deactivate it from here. I don't know why it's not taking it there. Right click, properties, deactivate. Now, go to properties. go to properties, double click on that rigid connection, select transmitted degrees of freedom. Do not include rotations. I will show you that you will have to come back and take rotation about Z included. I will show you, okay? And on the very top, if I run it now, it will work. But then what that means is on the top, it's not a cable anymore. It's kind of welded. Let's run it. You'll see. This will work. There's no problem. Yeah, we can see that. However, it's not right. Okay? On the top, there should be no restriction about rotation. Okay? This is why I made a finer mesh so that you could actually see it. So let me deactivate that. Let me go and get rid of this clamp. Put a user-defined restraint, and on purpose, I'm just going to say X, translation XYZ. Now, what that means is that this can spin about this axis. Down here it can because I removed the degrees of freedom. Down here it can because I didn't fix it. And we're going to run it. It's going to bomb out. Because it says, hey, you can spin about that. So that's why I go to this constraint, this last restraint, and I include rotation about Z. Okay? When you do it clamp, it says cannot rotate about X and Y. We know X-axis and Y-axis. We know that is not the case because if it's a cable, it will. Now it will run. Yeah, and we get pretty much exactly the same result as before. Let me click on it. And the average material shading. Now, notice that because this is a cable, it just goes down. And of course, it can also go left and right, but there's no restriction on that rotation about X and Y-axis. If you make a clamp, it will not rotate about X or about Y, but that may not be the case. They just stretch it. If this was, if we had not released the degrees of freedom and that didn't do this thing correctly, it would actually bend. Just to convince you, there we are. Let's go here. Make all of them fixed. Let's go down here to properties. Include the transmitted, is this the one? Yeah, include the transmitted degrees of freedom. And if you run it, you see that it actually bends. That is not how cables behave. Okay, you can see that. There. You can see it there. All right, folks, so that takes care of this problem. This problem, once again, I'm going to do it tomorrow, but in terms of an assembly. Okay, the choice is yours which one you want to do. Good luck.